go back
to that now. But the other project I'm doing is it's a power protection unit, and you can see also Carlsen has one, but I didn't like the tweaking.
this project. I need a stable voltage source, and I don't have a voltage source, so I've just used a LM317, and I can adjust it within a given range between these two here. Here's my setup, and it's just a preliminary setup. I connected a fan to the relay, so you can see that it switches on and off if the voltage is too high or low. So on the display here, this is the voltage output of the regulator, so that indicates the voltage from the power supply of the Commodore 64 though. So let me adjust it, and right now I connected it such that the fan will run if the voltage is below the upper limit. So let's see what's happened here. It stopped, and if I go back, did you see that the voltage bounced up? So let's try it again. About 3.3 volts or something is where it turns on again. Check that out. It jumps up about 10 millivolts. So basically what I've done is I have the TL431. It's like the scenery with the reference. And I have the voltage divider here set such that at 5.3 volts up here, the VCC or the power in, and that's 5.30, what is it, 35 or 34, then this device will then turn on, and then the voltage here, because of this division, will be 2.5 volt. So, and all of this is connected to ground though. So, and then I have the relay that what I did here, I connected the coil of the relay to have its return pass through this one, and it's okay because this device can handle 100 milliamps, so no problem. And then you have the air inside the relay, and let's draw the relay like this. You have the connections, looks like this. So what I've done is I've connected the 5 volt here, and I think I've connected the fan here. So yeah, so this is supposed to be a fan though. So yeah, so that's the fan. So when the voltage is too high, then the relay turns off or on, I don't remember. But anyway, this is not very good though, because this device, when it turns on and off, and depending on the voltage here, and it's not perfectly sharp as I thought it was, and also it doesn't go all the way down to 5 volts here. Sorry, this point here doesn't go all the way down to 0. This is when the power is okay, this part here is off. And out here we want a relay to be on when power is okay. So PSU okay, then this one is off and this one is on. Right? So how do we do that? And there's also another problem that we saw, that the voltage here doesn't drop down to 0 whenever this turns on. If you have like a NPN transistor here, maybe you can't turn it properly off. The idea was here to shut this transistor off when that one turned on. But the problem is that the voltage here drops to like 2 volts and then it's not properly off. Oh. That's a very typical problem in electronics. So we must avoid that. Well done. Then we can use a P-channel then. So when this one is off, then this is also off, and we can then just invert it. So now we can have our so now when this one is off, then this one is off, and then this relay should be on, right? So therefore we must have another P channel here. And why? Why, you may ask? So let's try see what happens. Let's say it's 5 volt here. So the power is okay. Then the power is okay. The voltage here is below 2.5 volts. And then 2.5 volts low. Then this is off. And then the voltage here is high. So then therefore this is off. And if this one is off, then the voltage here is pulled down by that resistor. And that means this is on. So off, off, on, inverter, remember? So off, off, on, and therefore this is on. So if the PSU is okay, then this one is on. And also the voltages here are properly zeroed when it's off though. So that's what we have, the problem we had earlier. Now let's say there's something wrong with the power supply and the voltage now jumps up to 11 volts or something like that. Then the voltage here is above 2.5 volts, and that means on the reference input, that means this device will turn on. So the voltage here will be dragged down much harder than this resistor can pull up though. So the voltage here is like 2 volts. So that means you have like 11 minus 2 volts, 9 volts over this. So this is on. Okay, so this is on, then this is on, and it's inverted, so then this one turns off. That's what we want also. Then we are protecting that coil from that 11 volt. And also, when this turns on, then this switch is then resting here though. So the voltage out isn't coming out. So I don't have this P channel. So what I've seen in the schematics is that you could actually just connect it directly to, like this though, directly to the, what is this called, the relay. Here's the relay, the contacts and everything, like this. So this is the relay. You can do this. So when the PSU is okay, then you have a low voltage here, which this one is off, and when this is off, then this voltage here will be pulled high, and this one is now on. And then you have 2 volts here. So it's not ideal though, because if the voltage is okay, then you have 5 volt here and 2 volt there, so you will have 3 volts over this. It's not perfect, but it will work though. So okay, you can see I have a second TL431 here, and basically what I did is just what I talked about in the schematics, like this. What I have the coil here. So, and it works very well. So if I now turn it up slowly to 5.35, so okay, let's slow down. See that? The voltage jumped up. That's actually great because when we were adjusting the pot here to get the voltage above the threshold, then when this switch off the load, the fan there, then the voltage jumped even further up, so that the threshold was leaped, sort of. Instead of just going over the threshold, we jumped over it, so that's okay. And I can show you what happens if you do the opposite. So now that's what I'm doing now. I'm connecting the fan such that it is drawing power when it's not supposed to be drawing power. So when you have a... Oops. This freaks me out every time. Now we have an over voltage situation and the fan is on. This load is turning on, or off, sorry, off. And when a load is turning off, the voltage will then jump around. So I think this this fan is putting some energy back into the rails. So just for fun, I added a capacitor on the reference input. So that means that the reference should go jump up and down slower. But what do you think happens then? It's much worse, because then it's jumping up and down a bit slower, so it gets hammered in here. Okay. Okay, so I have my scope hooked up to the output of the regulator, so it's on the 5-volt rail. And it seems that I don't have enough bypass capacitors. You should always have your bypass capacitor with you. As you can see, I have over here I have 1 volt per division in channel 1, and I have 2 microseconds per division, and you can see it drops about half a volt whenever whenever that fan is passing the switching. If you know how fans work, when they are rotating, they're switching on and off a set of coils, and then they produce a spike of current. So there you can see there's something going on there. And if I now bypass it, you can see that it gets a little bit smaller, and now if I pull it out, it gets larger. So obviously there's some I need some bypassing. No? It's still cranky, so you can hear it screaming. Weird stuff. But at least 5-volt here is okay. Oh, jeez. Oh, look at that, that's beautiful. Let's switch it on. And let's switch it off again. Check that out. So that's, what is that? That's probably the fan is regenerating energy back into the circuit. And I think maybe that's the problem, actually. So how do you solve that then? Well, I think you will have to stabilize that reference. Sorry for this device. So, and also now if I connect the fan in the way we're supposed to, then we don't have that problem anymore, because then well, okay, it's not perfect as you can hear, but we don't have the same rattling noise anymore, because I think the voltage is working in the direction we want, because when the reference is increasing, then it should pass the reference voltage, threshold voltage, and then when it shuts off, the voltage will jump even higher, so it will help us. It seems to have solved that rattling noise. Now it's more like bam bam when it goes on and off, so definitely bypassing is a good thing, but still I don't think that's enough. So what we want to see here is that this reference point, when it switches, it will give us a jump, such that it must be more effort to get it off again, so it just doesn't bounce around, because you can see there is noise here. So we have to take that into account also. Problems. So let's try and add the high hysteresis. So when you're talking about hysteresis, we have, let's say you have the output voltage on this axis, and you have the input voltage on this axis. So when the input voltage is low, then if it's an inverter like we have, then the voltage is high, and then when you reach a certain threshold, then the output should go low. And the problem is when we are setting our input to very close to the reference or the threshold voltage or the reference voltage, and then the output will then go on and off very rapidly, because we have noise from the fan here, so it makes our input voltage jump around, because it's not a fixed point, it's actually bouncing around in a certain volume here. So therefore the output will then violently go on and off. So what we can do then is add the hysteresis, and that the thing with that is you feed the output back to the input, the reference or the voltage divider. Remember the voltage divider here. So if we can feed something back here to make this sort of move with the output, so that it needs more effort to switch on and off. So what do I mean by that? Well, if you go this direction, then you have the reference here, and now since the output is now changed, we can use that change to move the reference. So let's say we move it so much that this volume in here, the noise on the input, that is the input voltage must drop more than before. So it must drop down here, right? So this is the direction this is going, and this is the direction that one is going. This can be done by taking the output. Let's say you have the measurement of the PSU 5 volt, right? And then you have some circuitry here. So this is our circuit cloud. And then on the output, this is a very good iPod. You can take this and feed it back. It must be in a positive proportion to the input. So if the input increases, so must the output though. So, or else it doesn't work. So yeah, that's what's happened. So no matter how slow this will increase, as long as it reaches the threshold, this very fast output will then make the input sensing circuitry change fast. So this is how you solve slow moving signals to get rid of noise. Get rid of noise. So and here's the ground also. Yeah, so that's how you do that. So, but do we have a? So if you look at ours, if this one goes up, this voltage here will go down, and the voltage here will then go up, right? that's great. We must have the same proportion, the positive proportional signal. And then we just take a resistor here, feed it back here. It's so simple. And we can calculate this until the cows come home. Oh, I'm starting to sound like EV block. I don't pretend to. So let's try that. And I will suggest 200k. I don't know why. I just want to try it.
Oh dear, he hasn't even calculated his resistors.
Well, I'm just doodling here, so we can calculate our resistors later. But for now, we're just making the topology here. So what I've done is that I have sorry, focus. You can see this resistor here is now going back to the reference input, so it's in parallel. Whatever was connected to the relay here back through a high 220k resistor, and these are like 4k and 5k or something like that. It doesn't matter right now, but the thing is that this one is much larger than these two. It's like 50 times larger, yeah. And how this works is that when this is off, this point here is then high, so we get feedback 5 volt on this side, and it will pull this point here up to 5 volt via this 2k. But since 220k, but this one is so weak, so it can't pull it all the way to 5 volt. It will just pull it a little bit. That's the thing. And now when this one turns on, this point here is pulled down to 2 volts, not 0, but 2 volts. Then this point here will be pulled down a little bit. So if it's close to 2.5, it will be pulled down a little bit lower than that. So yeah, so look at the screwdriver now. And the fan though. So there it's on. I'm moving it slow. Oh, there it turns off again. Let's go slowly back. You can see I already moved it a lot. So, and let's measure that on the voltage meter. So let's go up. Let's slow down. Now there. 5.34. Let's try it again. Yeah, 5.37 or something like that. And now if you move down, it's almost 100 millivolts or 80 millivolts below what I had to adjust before. I just now I removed the bypass capacitor on the 5 volt rail here, just to get those spikes from the fan back again. And we're supposed to protect ourselves from a faulty power supply. So, and now let's say this bypass capacitor is gone in the power supply, then this is not good though. So not sure what to do there. Maybe it's more bypassing can do it. Okay, so now I put a 220 nanofarad capacitor on the reference input and on the ground. You can see the ground loop there. This one, and then down here, and you have the reference there. So let's switch it on. And notice also I don't have that bypass capacitor anymore. And also another thing, if I don't have this one at least, then this regulator will then malfunction. So I must have something there. Because then it can get out of whack. No, I don't think I can get it to make that weird noise. So if I remove this now, you can already hear that something is wrong here. Yeah. and putting back the bypass cap here helps, right? And we also saw that by putting a capacitor to filter the input of the reference here, that also helped. So we'll definitely do that. So yeah, there's a short circuit here. So switch on. Okay, so the voltage on the relay here is not 5 volt that we want, because we don't have a p-channel transistor. So I'm sorry about that, but I think I will do it anyway. So I will try and make this circuit now and make it onto a protoboard, and I have connectors for it. And I have a couple of connectors there, one female and one male. Then we could go into the power supply, and the other one will go into the Commodore 64. This is what I got so far, so now we'll start adding connections, and we need some cable relief.
You want cables? You want cables? We don't need no stinking cables.
Check it out! I solder up this little circuit here, and I solder the contacts onto here, so I get 5 volt in. And here's the relay, and here's the cables that's supposed to go to the Commodore, but I have connected up this fan instead. So let's check it out. Now you can see the voltage coming in is 4.992. Let's increase that. And there is switched off. Let's add a fault LED. So I didn't find a red LED for indicating error, but found an orange LED, or orange LEDs. I think that will do, but I also found this one. Check it out. It's a Cree XPE RGB star. I almost said XPG, because I have those also in another project from ledtech.de. It's something I bought 5 years ago or so. Okay, as you can see down at here, the LED is in place, and the power is off. There you can see we have an over voltage situation, so the light will then start to glow. That's good, but let's not start it there. Let's wind it down to 4.998 volts, and watch the LED now. Do you see that? The reason for that is that normally this relay is off. There. Magic. Let's go back. Oh, by the way, shouldn't I have some sort of shunt diode on the coil? So okay, so inside this relay we have a coil, or an electromagnet. That's basically a coil with a metal bar in the center. So when that is energized, then you have a current path going down here, and when this is turning off, then this current path is broken. So but there's a magnetic field on this magnet, and that magnetic field will now collapse and it doesn't happen immediately. It falls down. So and also you can also think of it like inductors, that they don't like change in current. So when the current here suddenly stops, it will the voltage here will then rise very violently. So it can damage things that are connected down here. So what we do then is we want that energy from that collapsing magnetic field to go somewhere. So if we add a diode over here, let's say you had mounted it this way, that doesn't work, because now you have a short circuit going here now. So what you do is you mount it in reverse. So now when this device goes off, it makes an open circuit here, sort of. And then the current that did flow here then will go this way instead. So okay, so I discovered something that if I turn the power on and the voltage is like 5 volt exactly, then you have only 3 volt over this device. So because this pointer is held at 2 volt, so 5 minus 2 is then 3 volt over this. Sorry for this mess, but that's the coil. And I found out that if I do that, let's say I have 5 power and 40, and now if I disconnect it and reconnect it, and as you can see I get a fault. So, and I think what's happening here is that let's just focus. You can see I don't have to go all the way up to the threshold to make it start. Yeah, I think the voltage is only 3 volt and it's supposed to be 5, and it's around 3 volt when it starts. Okay, I have the Commodore here connected, Commodore power supply, so let's power it in and wait for the bang. So let's see what happens. Seems to be working. Now if I now pull it out, let's see what happens. Yeah, you can hear it tick, so seems to be working okay. The power saver, or the Commodore saver, is now connected, as you can see, and it's actually on right now. But if I turn it on, look what's happened. Yeah, so it's discharging. That's okay. And if I switch it on, you see it blinks, so that's fine. So if I now turn on the Commodore, the machine starts. So that's also fine. So, and I can switch it off and on. No problems. So that's working fine. So what I have tested like having the machine on before I switch on the mains. That also works, so no problems. So we'll keep it like this, maybe wrap some insulating tape around it or something. So yeah, hope you liked the video. So now I will be safe, I hope. So if something happens to the power supply down here, then this will then at least if the voltage will go too high, this will shut off the 5 volt also. Yeah, thank you for watching.